Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
This is Richard Jacobs with Future Tech Podcast. My guest today is involved with a company called Brainvivo.com. We're going to be talking about imaging technologies of the brain. How you doing?
Thank you. How are you?
Good. Yeah. Speaking of brains, mine was a little bit confused today, but if you would let listeners know what you do at Brainvivo. What do you guys do?
Brainvivo is the next generation of brain imaging technologies, which converts clinical MRI scanner into virtual microscopes. So our mission is to use our novel HD MRI-based non-invasive biomarkers to reveal new medical information based on brain microstructures.
And then what kind of brain microstructures? Can you give me an example?
Yeah. So if we think of the brain like a train station, so we have the stations and we have the tubes connecting each station to another station. So the brain composes of mainly of the gray matter, which related or resemble to the train station itself, and the tubes, which are the white matter. So we have the brain regions like the visual and auditory and motor, etc. And they transmitting information to other brain regions through the tubes or the cables, which are the white matter. So these are the basic brain elements. And when we're talking about microstructure, we're talking about the smallest element of the brain. We're talking about brain cells.
So, all right. So you were able to elucidate these structures. What are you able to do with the imaging that shows, essentially the plumbing of the brain?
Yeah, that's a good term. So up till now, if you want to see the plumbing of the brain, you need to take off the brain. I mean, you need to use a corpse and to dissect the brain from your body and then slice it and put it underneath the microscope, because the imaging technologies that we have today, and MRI is one of the best imaging today, or the most sensitive today, has a resolution limitation. So we can see changes in the tissue level and not on cells. And tissues mean hundreds of thousands of cells. And when a radiologist looks at an MRI image and you see some variation in the image, it is far too late because the tissue has been changed. We would like to see changes on cells, because if we can see changes of cells, that means that we can early diagnose brain diseases and disorders.
So you're able to see changes on a cellular level instead of an MRI, which only looks at whatever has happened or what's there currently. How do you do this imaging without being invasive? Like, what does the Brainvivo device look like, and literally where does it sit?
Okay, so basically we use a regular MRI infrastructures. So you can use any MRI you have today in hospitals, and we tweak the MRI. So we have our protocol. It's like a software that we can plug into any MRI device. And then we scan the brain differently than today routine scans. And we provide images that maybe will look a bit odd for the clinicians, but our software, we have a post-analysis software that knows what to do with this information. And we can extract this unique information and calculate the diameter of the plumbing. So what we are doing is like we can track water molecule movement inside the brain. And we all have water molecules inside the brain, so we don't need to inject anything. And we have a unique way, again, to tweak the MRI to be sensitive to water movement inside cylinders. So we can track the water movement and then its boundaries in the brain. And then we can quantify the axon diameter. The axons are the tubes, as I mentioned before. So we can measure the axon diameter and then to see if there is variation or degradation of those tubes, and that means that you have problems to transmit information from one area to another, and that can be a very sensitive neuromarker for brain diseases such as multiple sclerosis.
How early on is your sensing? If you disease in the brain, how far out in the future will that disease possibly occur?
Okay, so I gave the example of multiple sclerosis because this is the first degree disease that we started working on. And in multiple sclerosis, we know today that the disease starts somewhere in the age of puberty, but eventually it will be diagnosed between the age of 20 and 40. The average today is about 30 years old. And the thing is that the disease starts, you can see anything, not in imaging and not on the person's behavior. And only when it peaks after approximately 10, 15 years, the patient can have like neurological symptoms. He can be blinded for a couple of hours. It can be, have extreme pain, or half of the body you can't move it, etc. And when you go to the hospital, most of the cases will be sent back home, since multiple sclerosis should be multiple in time and space. So we need to come again because the doctor would like to see 2 attacks, not only 1, and also to verify that the attacks will be in different regions of the brain. So it's taken today approximately 4.5 years to diagnose MS. Our technology and our research that we conducted, first of all, we can see degradation of axon diameter of 20% in multiple sclerosis patients. But also we took a group that with high risk for MS, since they have a first onset, and they sent home, to wait for the second one. And we use our technique to predict who will be diagnosed as MS. And for our technology, we were right in 92% of the cases.
Wow.
So the bottom line is that we hope, to early diagnose MS patients and, cut the diagnosis gaps we have today. And MS is only the first disease we got into, and we're really facing other diseases as well.
What are some other diseases? We'll cover MS more, but what are some other diseases that you're hoping to find evidence of in the brain?
Okay, so for instance, we know that in Alzheimer's disease, it's one of the most, I think, known and discussed diseases today. In Alzheimer's disease, in the last 5 years, there are evidence talking about axonal swelling. That means that the plumbing or the tubes are being larger in the age of 40. So if we have the technique to measure the axon diameter in vivo in a living human brain, we really hope to find, and this is a research that we are already started to conduct, whether we can see axonal swelling in the patient that today are 40, but maybe in the future they will be diagnosed as Alzheimer's. And also Alzheimer's is a very hard to diagnose disease. When we diagnose Alzheimer's, it's in the late of 70, when half of the brain or half of the cells are already gone. And even if you have the best drug in the world, that medicine can't bring, can't revive the brain cells. So the key here is to early diagnose and then early treat.
Yeah, that's what I was going to ask you. For MS, for Alzheimer's, what happens if you can diagnose it years earlier? How much better can the treatment be?
Okay, so that's a good question. Today, our knowledge is based on what we can see today in clinical regular MRI scanners, and as I told you before, it's too late. So we are building drugs and medicines for what we can learn today or what we know today on the brain, which is it's far too late in the disease course. The ability to early diagnose will also open a new era of or new chance to develop new drugs for early stages, because we don't want to fight the disease in a progressed stage. We want to fight a disease in a very early stage that the symptoms are just starting to appear. We believe that with our tools, we can early diagnose and then learn how to fight a disease in the first steps.
That's amazing. Wow. Yeah, I guess part of the answer is we don't know what we can do, but we certainly can do a lot more if we see it early on. That's great.
Yeah.
So for MS, it's possible to diagnose it up to what, 4 years earlier? More than that? Less than that? What are you seeing?
Yeah. I mean, the average today for MS diagnosis is 4.5 years. And there is like MS-like disease, such as Lyme disease. 15% of Lyme disease will be diagnosed as multiple sclerosis. So Lyme disease is a disease that's caused by an insect.
Right?
Yeah. That eventually, if you do imaging to the brain, you can see lesions, and those lesions are white dots in the MRI image, and that's look like multiple sclerosis. So it's very hard to diagnose or to distinguish one by another, and the treatment is not the same treatment. So we would like also to bring innovation and better practice, not only for MS but also for MS-like diseases. We're talking about more than 10 million people around the world that's suffering from multiple sclerosis or other diseases that needs to be better diagnosed. So in MS, we hope to, first of all, to reduce the time of diagnosis from the first clinical onset, which will reduce the time from 4.5 years maybe to, a couple of months. But also think about people that have high risk for MS, such as family or daughter or mother or father of a patient who has MS. If we can scan them, to know whether they have a high risk to be MS, and then to monitor them or not, that can be very, very good for those people. Also, to do monitoring. Today when you are an MS patient and the doctor give you a drug, we don't know if the drug is good for you. We just need to wait to the next onset. And then if your next clinical onset will be severe or sooner than we expected, then we will replace the drug. We don't have any sensitive monitoring today to say to a patient, the drug is good for you, or let's change the drug. So we also hope that our techniques will be the first sensitive monitoring for those patients.
Oh, very interesting. All right, the scan is, you said it's essentially the same as an MRI, a traditional one.
Yeah. Except
it finds different things. It finds smaller structures.
Yeah.
Okay. So it's not invasive to do the scan, and if people do multiple ones, that'll work.
Yeah, I mentioned that. I mean, we talked about the MS, but in any brain diseases, eventually patient will go through MRI scan. So you don't need to bring the patient, specifically for the scan. They are needs to go through MRI scans to do the routine scans, and you need only to add like 5 minutes scan, which is our scans, in order to find out what are your axonal status, meaning what are the status of the brain plumbings. So we can know whether you are in the range of healthy, or maybe in the range of MS, or in the future maybe Alzheimer's or other diseases. And I just want to add that our neuromarker is not solely. You do need to have the patient history or other tests, etc., etc. But we do see that our information, unique information, can contribute to the clinician in order to early diagnose patients. So you just need to add 5 minutes to a regular MRI scan, and we can do our scan in any MRI infrastructure in the world.
That's great. I mean, it sounds like even, you're going to learn things about the structure of the brain that you didn't know before, even beyond disease. I mean, it sounds like it can be used in many, many different applications. Are you going to be licensing this to scientists that want to be able to use it for just to study the brain and its structure?
The answer is yes. Both me and obviously Professor Asaf, that works years in academia. We know that the one of the best way to improve the technology and also to spread the rumor is to allow the science and researchers to use it freely. And this is one of our first intention, to give it to anyone that would like to test our technology. We are a small company, we are a startup company, so our resources are limited, and we really want to use the power of research and our collaborators around the world to use these techniques on a various of diseases. That way, first of all, we can learn about the brain in a new way, and also we can gain from that, learning on our technology in multiple indications. So yes, we are willing to give it away free for research, and we are always looking for collaboration in the industry.
Yeah, that's great. Where is the most intense interest coming from? Are you getting inquiries? Do other companies and researchers know about this? How public is it?
Yeah. So first of all, our technology last year in 2016 has awarded one of the most important work in multiple sclerosis in 2016. And this year, a month ago, we have been chosen as a finalist in a conference called BrainTech 2017. And that's only one of our aims, to get out. But also, most interesting coming from pharmaceutical companies today, companies that develop medications, drugs in the MS field, but not only. We have now interest from the Parkinson side, because companies really want to understand what the drug are doing to the brain, as I told you before, brain microstructure, to the cells. The ability to learn and to know what the drugs are doing, the baby steps of the drug, will help the company to fine tune the drug and maybe to play or reduce its dose. And this information is very important to those companies, especially in phase 4, meaning after the drug being approved by the FDA, they're looking for clinical evidence that the drugs are working correctly. So our neuromarkers can help them to understand whether this patient or another needs to have more of the drug or less, or play with the doses, etc. So most of the interest comes from pharmaceutical companies, but we're also working with a medical devices company that has invasive devices for epilepsy or Parkinson, as I mentioned before, and they have all kind of challenges that need the support of very sensitive imaging to help them to track or identify the exact location that we need to be working on.
Okay. Any particular again interest or inquiries that you've gotten from outside companies or researchers? MS, very, very important. That's big. Alzheimer's. Anything else that you've had the idea where this could be used, or someone else has had the idea and you think it would be very impactful?
Yeah. So first of all, we really want to be in the same place that heart diseases were like 6 years ago. Because 6 years ago, heart one of the leading causes of mortality all around the world. And then by covering biomarkers such as blood pressure and obesity, etc., we learned a lot how to prevent heart attacks. And today, when you are in the age of 40, you're going to a family doctor, and he will prescribe what he needs to prescribe in order to prevent your heart disease. The same thing we would like to do to the brain, and this is why we are collaborating with various MRI companies to embrace our technology inside MRI scanners, and then to try and to learn and to find new neuromarkers using our technology that eventually, when you will be 30, 40, 50, yeah, you will go to the doctor and you will go through an MRI scan. And then from the MRI scan and from the images that we can provide related to your brain cells, we can know your brain status, both on the gray matter scale and also the white matter scales. And we can predict various diseases and also maybe to advise you to do this, that, meaning also medication, but also maybe to change your nutrition, reduce stress, etc. So I really believe that we are going this way, and this is why the MRI companies are very, very interested, to be able to track and change the way that we are looking at brain health today.
What about people's perception of the scan and the results? Right now, if God forbid, if you were scanned or I was scanned and they said, it looks like there's early signs of Alzheimer's or MS, it'd melt your face off. It would really scare you. How do you turn this into something that people will want to do, or do you find that they want to do it anyway? Would they rather know rather than not know?
Yeah. So that's a good question. And then eventually, I can only say that, today, over 2 billion people around the world, that's mean 1 or 3, is suffering from brain diseases and disorders. And
really?
Most of us will be, 2 billion. And most of us, when I say brain diseases and disorders, it's, all the range. It's ADHD and epilepsy and schizophrenia and all the range of brain abnormalities that you can think of. So it's 1 to 3. 1 or 3 will be diagnosed, and when we will be diagnosed, it will be too late, because again, with our tools today, it's very hard to diagnose in early. So when I've been asked this question, and people ask me a lot this question, I'm telling them, guys, look at the room, okay? So look to the right, look to the left. One of you is suffering currently from brain diseases and disorders, and we don't know that because we don't have the tools. But if I will tell you that, I don't know, in 10 years from now, you can know that you have something, but you can treat it with medication, with nutrition, etc. Exactly as we're doing, for heart diseases. If you ask people today, in the age of 40, whether you will go to a doctor and do tests, if you have heart problems, I don't think someone today will say, no, I don't want to know. Because yes, we know that today heart problems are treated, and we know that we have good medication and good monitoring, and nobody wants to die from heart attack. But 70, 60 years ago, it was common, unfortunately. So I think that as the technology is evolving, specifically in the medical field, I believe people will like to know if they have high risk for brain diseases. And I really believe that in the next decade we will have the solution and answers to help those people.
Yeah, I guess now if you get sick with the flu, you don't assume that you're going to die, or some kind of cold.
Yeah.
But 100 years ago, I'm sure it was a lot scarier. Now you think, I'll just take medicine, I'll be fine. So perhaps it'll get to that point where, it's probably crazy to say, but I have MS. But I could just take these pills and I'll be fine, So maybe that's the answer. Maybe it won't be so scary because it'll be very treatable at some point in the future.
Yeah. And also, I think MS is a very, very good example, because MS is a disease that you won't be done. I mean, MS won't kill you, but MS is a disease that attacks the brain again and again and again. And each attack, you're losing your capability. So the drugs today trying to reduce and to postpone the next attack. And people have MS. All they care about, is to reduce the impact of the next attack and to try to postpone the next attack for 10 years, 15 years, etc. And today there are very good medications that exactly do that. So people don't die from MS, and people really want to know what the status of their disease in order to manage the disease. Today they want to have, the information and knowledge, not to leave it to the doctors. Obviously, the doctors need to manage the disease, but also today, because the information we have all around, internet, etc., people are taking control of their lives and of the disease. So I think MS is a very good example how to manage your disease, and really to try to understand what is the current status of my MS and how can I use this knowledge to live a better life.
That makes sense. And I guess, one of the last questions, which probably should have been one of the first, how was this idea first thought of? How did you and your cohorts figure out even to do this, to come up with this type of scan and find these structures?
Okay, so this technology has been started in 2004 with one of the co-founder, Professor Yaniv Asaf, which came up with this idea. And about 5 years later, I was joining Yaniv's team during my master degree. So I have the first degree in biotechnology, and then my master degree was in brain research. So my challenge was to take the technology, which was after a validation phase in excited tissues and in animals, and I implemented the methods in humans. And what we did, we took healthy people and tried to see whether we can measure the people axon diameter, again, the brain plumbing, but also to measure the conduction velocity, meaning the time taking the information to pass from one brain region to another, and to find out if we can find a correlation between the diameter and the speed. And this is something we published a few years ago. And then my question was, if we can do this or find this result in healthy, maybe we can take a disease that has issues with conduction velocity, meaning that the information is not transferring at the best rate. And this is where MS got into the picture. So during my master degree and PhD, I was also working in the industry. So I was establishing an MRI center in Tel Aviv University together with Siemens Corporation. And later, back then, I was also the vice president of sales and marketing at another medical company. So looking at the medical industry from the eyes of sales and marketing, but also looking in the eyes from academia as a guy who did his master and PhD, I noticed the gap we have, between the industry and the academia. And once we saw the result in MS, I quit my job as a VP of sales and marketing, and I told Yaniv, listen, we have something here, and I know that you as a researcher would like to to validate this method on every disease we have on Earth until you would like to take it out. But people need this technology, and we have to do it now. And this is when we also after we heard the neurologist and clinician showing this technology, they were amazed. And since then, we are. It was only, I think, 1 year. We have a lot of collaboration in hospitals and also neurologists that working with us. So the end users are happy, and this
great.
is the way we took it out from the academia into the industry.
Yeah, that's great that you've been so inspired by it that you put stuff aside to join the project and you want to get it out soon. That's fantastic.
Yeah.
What's the best way for people to learn more about the project and to possibly collaborate with you? Find, or where do they go? What do they do?
So they can just go into our website. It's www.brainvivo.com. There are some explanation about what we're doing and also the way to contact us. But they also can look for if you are from the medical field or you want to read some papers. So you can look for Asaf or Horowitz and axon diameter, and you can see all the publication we have on the methods. Some of it is also in the website, so it will be easy to find it also.
Yeah, and last question. What's your guess on how long until this becomes commercially available? I can get an MRI scan and get this added portion onto it to look at the microstructure of my brain.
So in our current phase, we are working with pharmaceutical companies first, to regain some resources to the company, and also working with pharmaceutical companies will strengthen the methods. So after this period that should be end in the next 2 years, we are going to approach hospitals. So I believe in 2 years you will see this method implemented in most, I hope, most of MRI scanners.
That's amazing.
It will be like building.
Well, this has been great. Thank you so much for coming and sharing this technology. And it's really going to be a game changer. So thanks again for coming. Thank you for your time.
Thank you so much.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.